That one was easy. Okay, what time is it? Okay, we got 7 minutes to go. This would be the part A of that question, so you would plug the numbers in. If that's the case, you would just get some kind of a numeric expression for it. Part B is more interesting. Part B would be a test quality, show work test quality, or extra credit, okay? Because this involves a few assumptions that you were already testing. So now I'm interested in the strength of the magnetic field inside. Okay, so I know that the radius of this is gonna be R, capital R. So what I'm interested in now is check to see which color we're using for the magnetic field. All right, so it's gonna be blue. All right, so now let's figure out the strength of the magnetic field on the inside. All right, so we got the magnetic field. And once again, this is your R, and this is gonna be your B. Okay, so we are interested in the strength of the magnetic field, where R is gonna be smaller than capital R. All right, capital R represents the radius of the wire. Okay, so how do we do this problem? Let me check to see what else we have. Okay, so what I'm gonna do is I'm gonna place my amperian exactly where the magnetic field is. So I'm just imagine that they are right at the same point. Okay, messed it up, but I'm not gonna change it. All right, so my amperian loop is gonna be at the same point. So this is gonna represent ds. Once again, the same argument, B and ds are in the same direction. All right, so we got the same BDS. All right, so the net current on the inside is going to be responsible for it. So no, I'm interested in the net current inside the loop. This is the current. This is the within the amperian. Okay, so this is going to be the current within the amperian loop, net current, versus this one. This is the net current inside the wire. All right, so this is the net current within the wire. All right, so the net current within the wire versus the net current inside the amperian loop. In this case, the net current inside the amperian loop is going to be a fraction of the current inside the wire. Okay, so as long as you make that connection, then we are good. All right. Okay, guys, let's move forward. All right, so we got the amperian loop. We're trying to figure out the strength of the. All right, so we are trying to figure out the strength of the magnetic field inside the loop. All right, so by using the Ampere's law, the net current inside the loop, the amperian loop, is going to be responsible for the circulating magnetic field. In this case, B is the one which is circulating. Okay, algebra is straightforward. All right, so once again, the vector sign in the same direction, so the cosine of the angle is going to be 0. Cosine of 0 is going to be 1. So by using the same argument as we did before, we will turn this into a scalar product. Once again, the strength of the magnetic field at a radial distance is going to remain constant. So here's the magnetic field. So I'm going to pull it out. All right, don't forget the primes. Pull it out of the integral sign. And once again, the line integral around the circle is going to be the circumference of it. All right, so we'll do a back substitution. And solve for B. Okay, so that's it. All right, so this formula is going to give us the strength of the magnetic field inside the wire. All right, so as you start to increase the radial distance, the strength of the magnetic field is going to get smaller. All right, so okay, so the initial assessment is, okay, let me just clean this up. When you increase the radius, you kind of expect the strength of the magnetic field to go down. Initially, that's the way it looks like. There's nothing special, except you have to understand that this is the current inside the loop, inside the amperian. So what we need to do is we need to express the current inside the ampere loop in terms of the total current. All right, so this I prime is the current within this region. So I prime is going to be a function of the total current within the region of the wire. So I is going to represent the total current. I prime just represents the amount of current here. Okay, so what do they have in common? Okay, so there's an underlying assumption here, and you guys were tested on this assumption, and not too many of you guys got this right, unfortunately. The current, does it flow inside the wire or outside the wire? The current flows inside the wire, guys. Why? There's no net charge inside the wire. There's no reason for the charges to be repelled to the surface. There's no net charge inside the wire. What you have inside the wire are the conduction electrons. Conduction electrons are free to move any direction that they want. When you set up a potential difference, you get them to move in the same direction. That becomes current. So the current moves inside the wire. So the current density inside the wire, that's the amount of current per area, is going to remain constant. All right, your solutions are sensitive to your assumptions. That's how physics is. All right, so number one thing that I want you to remember is, number one, the current stays inside the wire because there's no net charge inside the wire. There's equal number of positive and negative charge. Negative charges are free to move from atom to atom. They will remain on the inside. Underlying assumption here is the current density is going to be constant. So this will be constant. All right, so that's the reason why the conceptual understanding is very important. So that with that assumption in mind, and the assumption is that the current remains inside the wire, and the current density remains constant, then you can solve this problem. All right, so I have to clarify my assumption. My assumption here is that the current density is going to be constant. So the amount of current within the cross-section area of the wire, which is going to be J, this is going to remain constant. All right, so that's to remain constant. Only with that assumption in mind. Now you can solve the problem. Okay. So what do we know? We know that the surface area or cross-sectional area is going to be, generic expression is going to be this, pi r squared. It's just the generic expression. All right, so we're interested in the area. Now we can solve this problem because this is going to be constant. So this is the net current inside the wire. All right, just understand that we're looking at this A is going to be the large area that we're looking at. This capital R represents the radius of the wire. All right, A prime is going to represent pi r squared. Okay, so it's going to be the Amperian region within the wire. All right, so I goofed up. Okay, so for I prime. All right, so these two will cancel. And then solve for that. So what do we have? So it's going to be I prime. Okay, so that's the expression we came up with. All right, so let's just get rid of those two. Okay, so the next step is, all right, so this expression is going to get substituted into that one. So the strength of the magnetic field inside. It's going to be r squared divided by capital R squared. And then here's the total current. I'll just place it there. Okay, so there's going to be a cancellation here. Literally, the only variable that we have is this. So B is going to be directly proportional to R. Okay, so which means that the strength of the magnetic field is going to increase within the wire as you're moving radially away from the center. All right, because the amount of current also increases within that distance. All right, Nathan, give yourself 20 points for that statement. Okay, so if I were to draw this out, it would look like this. All right, so the strength of the magnetic field is a radial distance, function of a radial distance. All right, so the strength of the magnetic field is going to increase all the way up to the perimeter of the wire. And once you get outside, it's just going to decrease as the inverse of the radial distance. That's it. That's what we end up getting. Once you're outside, the strength of the magnetic field is going to diminish. Okay, so obviously you could do numerically, but I would want to see the work. All right, so we end up evaluating the strength of the magnetic field due to the current within the Amperian loop. We notice that the strength of the magnetic field is going to increase radially all the way up to the perimeter of the wire, and that's going to diminish once you're outside. So that's what we came up with.